Hello everyone, I hope you are doing well. I am the Mr.Rimon with you from United International University, Bangladesh. So let us discuss today's class. Today is basically our tutorial class 7. So tutorial class 7. In the last tutorial video, I explained how the NMOS transistor is characterized in detail and how to plot the important parameters using LaTeX or overleaf. If anyone missed that discussion, please go through tutorial 5 and 6 first because today's content is a continuation of that work. So in this segment, basically what we will see. So the outline of today's class is number one, extracting the .dat files for PMOS from Cadence. Extracting the .dat files for PMOS from Cadence. Um, basically, we will generate simulation data for the PMOS transistor in Cadence. Then we will export the required parameters such as GM over ID, GM over GDS, and then ID by W, FT into GM over ID, and finally FT. So these record parameters we will export into .dat format. These files will later be used for plotting purpose. So the second outline is basically the plotting the .dat files. Plotting the .dat files in LaTeX or overleaf, whatever. We will import the exported .dat files into LaTeX. And then we will generate our required plots such as different parameters versus GM over ID. That means different parameter versus run conductance efficiency. Such as, for example, GM over GDS versus GM over ID. And then say, for example, ID over W versus GM over ID. So like that. So every important parameter, basically we will plot against the GM over ID for PMOS. These plots are very important for GM over based analog design methodology. So basically this is the outline of today's class. In short, today we are shifting our focus from the NMOS characterization to PMOS characterization, and then learning how to properly visualize the extracted data using the LaTeX. So without wasting any of time, let's move on to the cadence. So we need to sketch this schematic at first. We are using here 45 nanometer bulk CMOS process, and here this is a PMOS. So if you see here, we're actually considering the length as a variable and the finger width also as a variable. And this voltage source is variable, which is VGS-P. VGS-P means PMOS, gate to source voltage. And this is our VDD, which is variable. And finally, we are adding here this voltage source like this. So whenever we put some or assigning some value in the variable of the width, this voltage source will store the value and give the corresponding width a voltage format. For example, we are considering our width 2 micrometer. So this 2 micrometer is equivalent to 2 microvolt. So this arrangement we need to make sure here. And then we call the variable here and set the minimum channel length and minimum width, and consider the VDD 1.2 volt and the gate to source voltage a arbitrary value. After that, we are using here DC analysis. We are using here DC operating points. If DC operating points, then using here design variable and select the design variable as the VGS-P because we want to sweep the gate to source voltage. And after that, we are giving the sweeping range here from 0 to 1, and sweeping type is automatic, and then click apply and OK. So that's how the analysis set up. And after that, we will extract this expression from our calculator. So also I am adding here my .scs file for the PMOS. So if you check here, so let's see the model libraries. Okay, fine, 45 nanometer, and then the simulation files. I'm adding here are the PMOS .scs file. So now if I disable all the plots and run the simulation, so what will happen? At first, go to the result browser and try to see the DC value. So you can see the .scs file is actually successfully added here, and we can see all the irregular values here. All right. So I'm giving here the width of the PMOS is 120 nanometer. So if you see the W, that means this wire value, how much value the wire can contain. We can obtain this from here by using plotting the signal. So this is equivalent to the nanovolt because we want to plot the ID over W. So in that case, we need the corresponding width value. So that's why we are adding here in this schematic setup. So this is very important. Anyway, so after that, now if you see the GM over ID, so this is the expression of the GM over ID, and this is FT into GM over ID. Just simply you use the calculator and extract those expression. And finally, now we will plotting now the uh, signals. Sorry, these parameters. So let's enable the plot and see. Let's try to see. So you can see that all the parameters is actually plotting against the VGS. So we need to plot against GM override, not the VGS. So this is possible to plotting all the parameters in cadence also against GM override. We will see in later how to plot actually this important parameter versus GM override in cadence. This is very easy, not so hard. So if you see the GM override, for example, so this is your GM override. This is actually changing with respect to your VGS. Similarly, if you see the GM over GDS versus VGS, you can see this is your GM over GDS. That means your intrinsic gain, how to change against your gate voltage or gate to source voltage. And finally, if you want to see the ID over W versus VGS, so this is your ID versus ID divided by W versus VGS curve. If you increase your gate to source voltage, your current will be increased. So your current density will actually increase here. So now we will do the parametric analysis for different length. I've already done all the analysis here. So if you see the parametric analysis, let's load the parametric analysis here. Already saved. The starting point is 100 nanometer and end point is 3 micro. And I'm using here linear steps. And the step value is 200 nanometer. So if I run the simulation, you can see all the variation of the parameters with different lengths. But the plotting is actually done against the VGS. This is the problem. So you can see the curve. Let's say, for example, GM over ID, this one. So you can see the plots the GM over ID for different lengths against the gate to source voltage. So now what actually we do, we will save the parametric analysis as a ocean script. So you need to be save this parametric analysis as a ocean script. So you will actually save this ocean file. Let's say, for example, tutorial 7 tutorial7.ocn. So just simply save this one and close it, and write here gedit tutorial7.ocn. So this is our ocean file. So we need to modify this a little bit, do some ocean scripting. It's not a very crude level scripting. This is very simple. I've already done the ocean scripting, and if you see that, you see here, we need not to be use this tutorial7.ocn. We can delete this one. Rather, I am using here this file. I already performed this analysis here. So here you can see that I'm extracting here all the parameters. Let's remove this one, the VGS I want to extract a more parameter here, VGS, VDSat, forward type voltage, GM over ID. All right. And then you need to be write this script here. So yeah, so you can write this program, and then it will actually contain the x-axis here. So this is actually indicate your x-axis value, and this will be indicate your y-axis value. So our GM over ID will be in x-axis, and GM over GDS and others parameter will be in y-axis. So after that, if you do the scripting run, then you can save it, and then you can copy it, and for example paste it, then go to rename, and then copy it, use a header backslash, and then paste it, and then copy all this, and go to your virtuoso, then use a load function, and then paste the ocean file with the appropriate address, and then hit the enter. So it will execute your ocean scripting into .dat format. You need to be patient and wait in this moment. So it will generate your .dat files. It will take some times because they're okay, fine. So successfully everything is done. So basically, this is our .dat files. PMOS, FTGM over ID, and this one, this one, this one, this one, and this one, this one, and this one, and this one. So you need to use these .dat files in a folder. For example. So I delete the all values because I already extracted those .dat files and create a directory here. And if you see the name of the directory, this is PM0 final .dat files. So all the values are here. If I let's open a .dat files, you can see all the values here. So now it's time to modification. We will perform some modification on the .dat files, and then we will export those modified PMOS .dat files into LaTeX, and then plot those in LaTeX. So let's go to the Windows. So you actually simply copy this directory and go back to your Windows environment, and then simply paste it. So these are my original dot files that I'm exported from Cadence. If you see the FTGM over ID versus GM over ID dot dat files. So these are actually my original value. So we need to modify this one. So in that case, I am open just one modified dat file. For the similarity, I'm using here the FTGM over ID versus GM over ID .dat files. So this is my modified dat files. You can see I am just changing my column header. Here you simply remove this column and this column, and after that you will actually write this column here. So you need to be write this column here. So by using our parametric analysis length, I am considering the maximum value is 2900 nanometer for FPGA over ID and for GM over ID. So that is the modification you need to consider for all the parameters. If I open another modified get files, for example, GM over GDS versus GM over ID, in that case, you can see the similarity is here. So you need to be do this modification. This is very necessary. If you cannot to be able the modification properly, you cannot plot those dotted files in LaTeX. All right, so just a reminder for this very important information. All right, so now I am in my overlay account. So I already uploaded my get files here and plotting the FT-GM over ID versus GM over ID, FT versus GM over ID, GM over GDS versus GM over ID, and ID over W versus GM over ID. So if you see here, let's compile. Let's compile it. Okay, so you can see that this is your FT-GM over ID versus GM over ID plot. So this is for NMOS. So you need to be write the maximum and minimum value from your dat files. So if you want to see the value, we are using here FT-GM over ID versus GM over ID. So this is our FT-GM over ID versus GM over ID. So you see the minimum value of the, you can see the maximum value of the GM over ID here, which is 35. And GM over ID we are considering here in x-axis. So our x-axis maximum value is 35 and a minimum value is 2.3. So we are consider here the x-axis minimum value is 2 and maximum value is 40. Okay, and similarly we have y-axis minimum value and y-axis maximum value. So if you see here, the y-axis minimum value is 2.11 into 10 to the power 6. So I'm using here 1 e to the power 6. And the maximum value is 1.5 into 10 to the power 11. I am using here 1 e to the power 12. Okay. So that is why that's how you using the maximum and minimum value. This is very important. And after that, you are using here the x tick value and y tick value. So finally, this is your plot. So these are actually your x tick value. I'm using here 2, 15, 25, 35, 40. And y-axis value is like such this way, 10 to the power 6, 10 to the power 8, 10 to the power 12. And you write the code properly. If you write the code properly, it will execute this type of plot. And this is very crystal clear and very nice curve. After that, you see the FT-GM over ID versus GM over ID plot. So we need to compile it first. So let us compile it. Switch to PDF. So this is my FT versus GM over ID plot. This is for PMOS. Okay, so this is for PMOS. And let's try to see the GM over GDS versus ID over W plot. Let's switch to the PDF. So you can see the GM over GDS versus GM over ID plot. And finally, I'm plotting here ID by W versus GM over ID plot. Let's compile it and try to see PDF format. So this is ID by W, that is current density versus your turn conductance efficiency. That means the GM over ID. So that's how you can plot your dat files in LaTeX. It will give you a very nice and crystal clear curve. You can use this curve in your research paper also. So that's how you can actually plotting the MOSFET important parameters, and you can characterize your transistor, for example, your NMOS or PMOS. So we try to explain how to actually characterize the NMOS and PMOS in detail, and that's how you can actually using these plots in your design. So in the next video, I will show a design example, and the design example will be related with the GM over ID design methodology. And please subscribe my channel and keep with us and pray for me. And with these, conclude today's tutorial class. Thanks for watching.